Dimensional systems, wave functions are relatively easy to identify and characterize. This changes, however, when we move to 3 dimensions, and we're going to look at this in particular for the case of the hydrogen atom. Now, there's several ways that these 3-dimensional states are typically characterized. For example, one could represent it as a surface inside which the electron has a 90% chance of being found. Okay, and that's something that might be represented here as this sphere. That sphere represents, inside that sphere, the electron is 90% of the time, and only 10% of the time would it be outside that sphere. So it gives us an idea of the region of space that the electron inhabits. One could also use a dot density map, which is a way of describing where the electron is likely to be by the density of the dots displayed in a picture. And this is a picture of one of those. In fact, this could be the same state as the one drawn here, but you'll notice that the dot density diagram is able to give us a little bit more information because we're seeing some additional structure inside what would otherwise just be a sphere. One can also use cross sections, and the dot density plot that we've shown here is an example of a cross section of the hydrogen atom wave function, but there are many ways that one can do a cross section. Now, the shapes of these functions are largely determined by the locations and the types of their nodal surfaces. And to describe what I mean here, you'll notice that in some of these pictures, and especially this one that we've pointed out already here on the upper right-hand side, there are some places where there are no dots, where there's effectively 0 probability of finding the electron. And these represent nodes. So nodes are places where the electron isn't. That's sort of a backwards way to say it, but whenever we have a vacuum in space, that's where there's a node in these wave functions. Now, we can characterize these nodes in a couple of different ways, and so what we're going to typically do is distinguish between 2 types of nodes. The first of these types are radial nodes, and they arise whenever the radial part of the wave function goes to 0. So remember that the total wave function is written as a product of a radial part and an angular part. So when the radial part is equal to 0, this signifies the presence of a radial node. And since we have mathematical forms for these wave functions, we can determine exactly where those radial nodes might occur. So these are essentially their values of R that give rise to this condition. So they are specifically values of R, and remember that when we look at this at the spherical polar coordinate system, so I'll draw a 3-dimensional coordinate system down here, x, y, and z, that these coordinates are R is the distance to the point, phi is this angle in the xy plane, and theta is the angle relative to the z-axis. So the R here, when R is fixed at some certain value that makes the radial wave function equal to 0, that in effect describes a sphere. All right, so the surface in this case for this radial node is a sphere. It's a sphere corresponding to one of these values of R. All right, we also can have the case where we have nodes that are due to the angular part. So we'll call these angular nodes, and they would occur whenever the spherical harmonics happen to be equal to 0. So this is what gives rise to these angular nodes. And they might be characterized by values of theta and phi that cause this function now to be equal to 0. Now, they're a little bit more complicated to characterize than the values of R, which are, strictly speaking, spheres, so I'll save that for another video, and we'll just talk about the radial nodes in this case. But nevertheless, these angular nodes are going to be important in determining the shape of these wave functions. Now, when I talk about the radial nodes, so let's go back to that, we can see actually examples of the radial nodes in this upper right-hand corner. We've got a radial node here on the very inside, and it's hard to see with the colors, but there's a blue center, then a red region, and then another gap. So there's actually two radial nodes in this picture. But in effect, the radial nodes form concentric circles in these plots. So we would see those radial nodes appearing as a concentric circle. So here's another one drawn here in this particular wave function. All right, so it's easy to identify those radial nodes because they are concentric circles about the origin, which is the location of the proton or the nucleus. Now, when we draw the radial part of the wave function, and I'll do that here for a particular radial wave function, it might look something like this. So here's a picture of one of those radial wave functions, and this part here is where the node occurs. So it's at this value of r where that node would occur, and so that sets the size of the sphere in which that nodal surface will exist. Now what I want to do is I want to translate this picture now to another page and talk a little bit more about what sort of analysis we can do with that. So here's that same wave function drawn here on a different page, and I'll say that this particular wave function corresponds to the n equals 3, L equals 1 eigenstate of the hydrogen atom. So this would be the R31 of R wave function. Now, if I actually wrote this in terms of that reduced value or that scaled value of r, this wave function actually would have the following mathematical form. It would be 6 rho minus rho squared e to the minus rho over 3. Now remember, this rho was written in terms of r as r, it's zr, but I'll leave out the z, over n times a0. So in fact, this particular r is written in units of na0, but n is equal to 3, so that's units of 3a0. Okay, so if I solve for r that makes this part equal to 0, this part can't be 0, but I think it's pretty easy to see that a value of rho equals to 6 would cause this particular expression to be 0. So that's where the node exists. So this point would be at rho equals 6. Since rho is equal to 3a0, that means that the node is actually at a distance of r times 18e0 for this particular function. Now, this tells us something about where the electron is staying in the wave function, but it's not necessarily going to be a good gauge for where the electron is most likely to be found. I'll remind you that when we do probabilities, that these wave functions squared is a probability density. So if I was interested in how probable is it to find the wave function or to find the electron within a distance r, say, of the nucleus, so I'll draw that as p with less than r, then the integral that I would have to calculate to find this out would look like this. So we do an integral over all of the coordinates, d phi, d theta, and then you need to use the volume element for spherical polar coordinates with this. And then the critical part is going to be the radial part, which will be dr times its volume element. And then we'll have the wave function squared. Now I'm going to write that in two sections. I'm going to write the radial part squared and the angular part squared. All right, now if I move this angular part over here and do this integration over all these angles, if the spherical harmonic is normalized, I'm just going to get 1 for that. So the really critical element for this probability density, or this probability, is going to be to calculate this part, the dr r squared of r quantity squared. Now this r squared, it turns out, is pretty critical. So now if we think about what does that look like on this graph, that's a function that comes up like this. All right, so in other words, it de-emphasizes the early part of the wave function and increasingly emphasizes the later part. Now, because this later part has an exponential decay, it will eventually come back to zero. But if I were to graph this integrand, and let's do that here, what I would get is the following kind of picture. And maybe I better make this in terms of rho. So what I would get is something that looks like this. I would have a little part here that would come down and it would be back to zero at the node. So this is the node. And then it would come back up and it's going to be exaggerated up here because of this r squared part of the integrand. So it turns out that this part is actually a more probable place to find the electron than this inner place, even though it looks different over here when we just plot the wave function. So this is something that I want you to get used to detecting, is when we're talking about the probability of where to find the electron, we have that volume element in there that's going to change how things look. So even though I can accurately draw this wave function, I really need to look at r squared times the wave function squared if I want to get an accurate picture of where the electron is likely to reside.